Hey kids, we are back talking about volume today, but before we get to the calculus idea of it, let's just do a quick review of the geometry philosophy. Yes, I know it's bringing back good memories from freshman year here. So volume of a prism, and to do that, I actually start with a cylinder. Maybe that's the one you're most familiar with. That, the volume of a cylinder is pi r squared h. But just so you know, height, has nothing to do with how tall it actually is in geometry. It's about the distance between bases. And it's all about the idea that a cylinder is just a stack of circles. No matter how you slice it, as long as you slice it parallel to that circular base, it's just a stack of circles. And so you're multiplying by the height, which is the distance from first circle to last circle, to effectively get that compressed volume of all the circles added up. And so the same idea with prisms. A cylinder is really just a circular prism. If you have a rectangular prism, which is the easiest one people think of, they think of the volume as being length times width times height. And that's true. Length times width will give you the area of that rectangular base. And then you're basically just multiplying it by how high the stack is. It's like a big ream of paper. Anywhere you slice it, that cross section is the same exact size and shape as that bottom and as that top. So it's area of base multiplied by the height of the stack. You have a triangular prism. Again, height doesn't have to do with how tall it is. It's distance from base to base. And the cross sections that you're looking for that are congruent are triangles, right? No matter where you slice this shape is really just like a stack of triangles. And so it's the area of the triangle multiplied by the height. Pentagonal, it's just a stack of pentagons. Area of the pentagon multiplied by that height. Hexagonal, same deal. All hexagons multiplied by the height to get that compressed volume. So now what we're talking about is, well, what about if we have a solid that we know what the shape of the cross-section is, except that all the cross-sections are different sizes, unlike these. And that's what we're going to use calculus for, but it's that same idea of, if we know the area of the cross-section, can we just add up all those cross-sections? And so here's what the wording looks like. Consider the region bound by the graph of y equals x squared and g of x equals root x. Find the volume of the solid whose base is this region if its cross sections, if taken perpendicular to the x-axis, are squares, equilateral triangles, semicircles. So that sounds really easy, right? Can you visualize the solid it's talking about? Probably not, which is why we're going to go to a little demo here and hopefully help you visualize it before we just grind out the calculus on it. So without further ado, let's go to that demo. Okay, so check this out here. It's giving you a little 3D visualization of the problem, which here's the graph of y equals x squared. Here's the graph of y equals the square root of x in two-dimensional xy plane form that you're used to seeing. But the problem said to visualize this, consider this region as the base of a solid, as in the floor, the bottom of a solid. So now we're going to x, y, and z axis right here, going 3D. And see, this is the bottom of a shape, a solid, which is not shown yet. And we're going to find the volume of this region if we know what the cross sections are. And you'll see there's different options for each type of cross section. So just kind of watch this. It's hard to visualize, but this is a great thing here, and this is GeoGebra. It's kind of like a Desmos type thing where there's a lot of graphing capabilities and cool little demos people have set up. But in this region, for example, notice what happens here. As I'm moving this along here, this is just showing you that at the beginning of this region, this is a fairly small distance between here, this vertical distance, and the problem said we are going to take slices or sections that are perpendicular to the x-axis. So notice a very small distance there, and as I go more towards the middle, that distance gets to be a little bit bigger, right? And that's corresponding to over here. And as I get towards the end of this region, that distance starts to shrink again, and it's, you know, a very tiny little distance as I approach that intersection, but it's there, and then boom, there's nothing. So now we're gonna visualize that at each slice that I take along this line, what if the cross section is a square or an equilateral triangle or a semicircle? So we'll look at squares first, just so you can visualize this. And you see, if I click on that right here where it's, you know, a fairly small section, that segment, that distance there, is the side of a square that's like standing up on this. And as you go more towards the origin there where that distance gets shorter, the square gets smaller with it, because that segment is the side of the square. As I go more into the middle, the segment gets bigger, the square gets bigger. And now if you want to see the full solid, this is just showing you the one particular cross section at each x location, and that's what n here represents, is how many cross sections we're going to show. So if we show a bunch of them, now watch, you'll see the full solid as you go along. And you see it's sort of piling up those squares, and they start small, and you get that kind of curved dome, and then they're big in the middle, and now as you start to get towards that end, they come down again, and you get this kind of funky dome-shaped thing. It's kind of like an irregular loaf of bread that you get from the bakery, but if you're slicing it, you know, if you slice towards the end, you get little short slices. You slice in the middle, you get the biggest slices possible. And so that's the idea. How do we get the volume of this? Well, if they're all squares, if I can get the areas of all those squares and I add them up essentially, which is like multiplying by the height does, then I get the volume. How do I get the area of every single cross section? I mean, there's an infinite amount of cross sections. So that's where the calculus is going to come into play. And now you can visualize that, well, what if the cross sections were something not squares, but equilateral triangles? So I'll move back to the middle here, where you got sort of like halfway through the loaf of bread. What if it wasn't squares? What if it was equilateral triangles? And so you can see there, it's a similar kind of loaf of bread, except it all comes up to a single point there on the top, and it actually makes it appear as a smaller volume altogether. So when we get that volume, it should be less than with the square cross sections. Right? Pretty cool though. Right at the end, small section, small triangle. And with semicircles, this one is actually an important idea when we get to it in a minute. The important thing with a semicircle is that, and for all these problems, it's about, well, what does this segment here, what does this distance represent? For a square, it's the side of the square. For an equilateral triangle, it's the side of the triangle. For a semicircle, this segment is the diameter of that semicircle. So that's important, because when you're going to talk about finding the area of it, we know the area of a circle is pi r squared, so we'll get to that. But I wanted you to visualize it first. And, you know, as you add more cross sections, you know, there we are. It's like halfway through the loaf of bread, but it's like a nice smooth dome. And look at how small that really is compared to the square one. You know, they all have the same base, like the same bottom if they were, you know, baked in the same pan. But look at the square one is so much taller, so it should have a much bigger volume. But anyway, hopefully this helped you visualize what we're going to find. Now we'll do the calculus of it in a minute. But it's all going to be about finding the area of each of those cross sections and adding them all up. And maybe you see where that's going, because adding up an infinite amount of things, that's what integration's about. But all right, let's go back and grind it out with some algebra. Okay, we're back. What'd you think of that transition, John Lee? Pretty sweet, right? Okay, well, now let's get down to this here. A couple things here. First, maybe it's obvious to you where these two graphs intersect, but if it hasn't been given, you know, you should always show that work. You know, so getting your intersection would be setting x squared equal to root x, or f of x equal to g of x, and then solving. And this one, I think you know the solutions are 0 and 1. Feel free to solve it algebraically, graph it, intersections, whatever. But our solutions are at 0 and 1. The other thing that's important, regardless of the cross-section, hopefully you made this connection, is that this vertical segment, which again is going perpendicular to the x-axis, that's what's important about that, telling us we're taking our slices in this direction, or like when we did our Riemann sums, our rectangles are vertical, which tells us we're going dx when we set up our integrals. But this segment, whether it's here or here, that dictates everything. That dictates the side of the square, the side of the triangle, the diameter of the semicircle. So you want to find a way to describe that distance, and that distance is the distance between this top curve and the bottom curve. Now this curve is the square root of x, that's g of x right here. This is x squared, that's f of x. Regardless of whether it's a short distance or a long distance, that distance is always the difference between g and f, right? So that would be, I'll just write, distance equals g of x minus f of x. And that's, again, top minus bottom to ensure a positive distance here. So regardless of where I'm at, the difference in these y coordinates, g of x minus f of x, top minus bottom, describes that distance. Okay, so squares, you do not have to do this here, especially when you get good, but I like to try to draw it a little bit in 3D now that you've seen it. It's kind of cool. And so there's sort of the 3D element here. There's the z-axis, and we've got our parabola here. I'm trying to draw this as if this is a tabletop, and there's my square root of x. And my sections are looking like that. And when I do it there, I have a little square standing up. When I do it there, I've got a bigger square standing up on the tabletop, and there a little tiny square, and there an even tinier one. But here's the idea for all of this, is that try to describe the area of that particular cross-section. Now, every square, the area of a square is side squared. And what is the side of each one of these squares, no matter where I'm at? It's that key distance, the g of x minus f of x. So for these particular squares, every side is g of x minus f of x. So every area, the area of every one of these cross sections is going to be g of x minus f of x squared. Or if you'd rather write root x minus x squared, you want to write the actual algebra. Of course, that's fine too. And that describes the area of any one particular cross section. Well, if you want to get them all, in other words, to get that volume of the whole thing, that's what we get. That's where we bring in the integral, right? It's just like when we started adding up an infinite amount of rectangles to get area. Well, now I'm adding up an infinite amount of areas to get volume. So if you can describe the area, and mine is g of x minus f of x squared, that's one square, then I'm going to integrate with respect to x, so dx. And what are the boundaries of my region? From 0 to 1. This whole problem, it's gone 0 to 1. And when you do that integral, that's your volume. Very cool, right? So you could do that one by hand. Root x minus x squared, square it out and integrate, that's fine. But you also are welcome to use the calculator. I've already put them in y1 and y2. I put g of x as y1. And so here we go. Math 9 here brings us that definite integral from 0 to 1 of, I want to make a new set of parentheses in there because we've got to square it. So that would be y1 minus y2, close, square, with respect to x, And this should give us the volume of that solid. This seems a little disappointing, right? You think it'd be bigger, but you're only going from 0 to 1. And those, those squares aren't really that big. So you get about 0.128 or 129 again. I'm a rounder, maybe you're a truncator. Okay. So how does it change things when we change the cross section? If you like to draw the diagram, there's the x squared, there's the root x. When it's that section, you get a sort of a medium, a mini triangle. Slightly bigger triangle standing up. At the front, tiny little distance, tiny little triangle. You just got to describe the area of one of those triangles and then integrate. Now, the area of any triangle is 1/2 base times height, but you should, or it's nice to know that the area of an equilateral triangle has a very specific formula. Maybe you remember this from geometry, or maybe not. S squared root 3 over 4. That is the area of any equilateral triangle. You can derive it using 30, 60, 90s, which you get anytime you drop an altitude down the middle. But if that's the area of any one of these equilateral triangles, just keep in mind that that side that it's referring to is that same distance that we used here, that g of x minus f of x. So really, this is going to be g of x minus f of x squared, and times root 3 over 4. Okay, and so now if that's the area of one of those triangles, if I want the volume, I integrate to add up all the triangles. So I'm still going 0 to 1, and I'm doing this right here. It doesn't matter where you put the root 3 if that looks a little ugly. You can have root 3 over 4 kind of as a coefficient of this, and that brings up actually another little point that's nice. And you're going to see in a second that, yeah, there's the s squared root 3 over 4, integrating from 0 to 1 to get that. Now, if you notice, this is nearly identical to the integral we just performed, with the exception of the constant multiple of root 3 over 4. So if you want to be smart about it, it's going to be the same answer as this, just multiplied by root 3 over 4, right? Because we can factor out any constant multiple. If you don't trust it, of course, by all means type it in again, but I'm just going to take the last answer. And I didn't want to use the rounded answer because, it wasn't the final step. So I want the most accurate before I round, and that would be 0.055 or 0.056. And yeah, remember we looked at that demo online and said it's a fair amount smaller. You could see it was smaller when you use triangles, and so I should be getting a smaller volume. And if you remember this should be the smallest volume of them all. Semicircles here. There's the parabola, there's the square root. When you took a section right in the middle, remember that was the diameter of a semicircle, sort of standing up like a little dome, like a little shell on the, like a little, I don't know, a little turtle or a little slug here. Slugs don't have shells, but whatever. So the area of a semicircle is what you want to try to describe. If you can describe the area, you integrate it. The area of a semicircle is 1/2 pi r squared, right? Or pi r squared over 2. Just keep in mind, for these semicircles, that distance that we keep using over and over again, that's the diameter. So you've got to take a moment and define the radius as half of that before you square it. So I've got my pi over 2. I just kind of took that out in front. And the radius that I'm going to square will be g of x minus f of x divided by 2, and that entire fraction squared. And some people will leave it like that when they go to the volume. Some people will play around and take the pi over 2 out in front. There's all kinds of little things you can do if you're comfortable with your calculus properties. But here's at least the main idea is, if that's the area of one of those, integrate to get the volume of all of them kind of compressed together. And so g of x minus f of x over 2 squared dx. Definitely you can type it in right now like that. If you do want to get a little clever here, not only can you factor out pi over 2, but you could say, you know, squaring this would be like squaring the numerator and squaring the denominator. And that denominator would be 4. And I could factor that out along with the pi over 2. So if you like, if you feel comfortable, you could say, you know, this is going to be the same thing as pi over 8. Pi over 2 times that 1/4 times that g of x minus f of x squared, which is the same integral we just did. So you could save yourself a little calculus time here. Just going back to that same integral of that squared, and now multiply by pi over 8. And yes, you get the smallest volume yet of 0.050. And that's that. And so the big takeaway here, and these were just 3 classic kinds of cross sections, but of course the cross sections could be other shapes. They're not always these 3. But the main idea is that if you want the volume, you're going from A to B, it's all about the area of that cross section. Whatever kind of cross section you're dealing with, describe that area and integrate between those boundaries, and that gives you the volume. And going perpendicular to the x-axis, that's dx. So take a guess, if we were going to the y-axis, that would be dy, and that'll be tomorrow. But all right, so hopefully this made a little sense. It's a tricky topic, but hopefully you can visualize it a little bit. And if you have any trouble, of course, just ask. Hang in there.